Welcome to this guide on HDFS Storage Management. In today's data-driven world, Hadoop Distributed File System, or HDFS, must efficiently manage both performance and cost. To address this, HDFS supports a variety of storage tiers, each tailored for specific types of data and workloads. By aligning data placement with access patterns, such as frequently accessed hot data or infrequently used cold data, HDFS improves both responsiveness and resource utilization. The key storage policies include disk as the default for balanced workloads, SSD for high-performance needs, and archive for cost-effective long-term storage. Each storage type has its own unique media characteristics and policies that define how replicas are distributed across the cluster. Let's take a deeper look at the primary storage types supported by HDFS. Starting with disk, it uses traditional hard drives and offers moderate throughput at a low cost, making it the default choice for most workloads. Next, we have SSDs, or solid-state drives. These provide high input and output operations per second, ideal for latency-sensitive jobs, though they come at a higher cost. Lastly, archive storage relies on high-density hard drives or even tape. It offers the lowest cost per terabyte but is optimized for low throughput, long-term data retention. Importantly, all three storage types ensure high durability, maintaining data integrity over time. Now let's explore some performance metrics and ideal workloads for each storage type. Disk is well suited for approximately 80% of typical HDFS workloads due to its balance of cost and throughput. SSD offer 3 to 5 times faster read and write speeds than traditional disks, making them ideal for jobs that are metadata heavy or require real-time responsiveness. Archive storage, while 5 to 10 times cheaper per terabyte than disk, delivers throughput under 100 megabytes per second. This makes it an excellent choice for archival datasets that are rarely accessed. Now let's discuss practical use cases for each storage tier, beginning with SSDs. Due to their high performance, SSD are ideal for real-time analytics and small file workloads. They're especially effective in scenarios that require high-speed access to intermediate data, such as during Apache Spark Shuffle operations. By storing temporary or frequently accessed intermediate results on SSDs, you can significantly reduce job completion time and improve overall system responsiveness. For general-purpose workloads, disk storage remains the go-to option. It's well suited for large-scale data processing with MapReduce and for hosting structured data in Hive tables. On the other hand, archive storage is ideal for datasets that must be retained but are rarely accessed, such as compliance data, audit logs, or historical backups. A common example is moving sales data that is more than 2 years old from disk to archive. This transition frees up active storage and reduces overall costs. HDFS comes with several predefined storage policies that determine how data replicas are placed across different storage media. These can be set using the HDFS command line interface. For instance, to assign a policy, you might run a command like HDFS Storage Policies set storage policy path/data/finance policy all SSD. Let's review some key policies. The HOT policy places all replicas on disk and is used for highly active datasets. Cold stores all replicas in archive, ideal for long-term storage. Warm distributes data across disk and archive, perfect for data transitioning from hot to cold. Finally, all SSD ensures all replicas reside on SSD for maximum performance. To manage and rebalance data across storage tiers, HDFS provides built-in tools. The Mover tool migrates data from one tier to another, ensuring storage policies are enforced. Meanwhile, the Balancer redistributes data within the same storage type to maintain even space utilization. These tools work together to keep your storage infrastructure optimized, efficient, and aligned with your defined policy goals. To leverage HDFS storage policies, configuration begins with enabling support for multiple storage types. This is done within the HDFS site XML file. A typical configuration might look like this. Set the DFS data node data dire property to specify paths for each storage type, such as disk, SSD, and archive directories. This setup informs each data node about the physical layout of its storage devices, enabling intelligent policy enforcement. Monitoring the effectiveness of your storage strategy is crucial. You can use the HDFS CLI command HDFS dfsadmin report to view usage statistics. Alternatively, the NameNode web user interface provides a graphical overview, including volume, utilization by storage type. To execute policy-driven data migrations, run the mover tool with a command like HDFS mover/data/audit_logs pcode. This migrates the target directory to the specified storage policy. Effective storage management in HDFS requires thoughtful planning. Allocate SSD storage for 10 to 20% of your data targeting performance-critical datasets. Use archive storage for 40 to 60% of your data to optimize for cost. Apply the one policy for datasets that are gradually cooling down. Avoid placing large, sequentially accessed files entirely on SSDs, as this leads to unnecessary cost. For seamless lifecycle management, consider automating tier transitions using Apache Atlas or custom scripts tailored to your data workflows. To summarize, use SSD for performance-sensitive tasks. Disk storage is ideal for everyday operations. Archive storage is best suited for long-term retention. By intelligently applying HDFS storage policies, you can reduce total cost of ownership by 30 to 50%. Your next steps include testing these policies in a non-production environment and automating data movements using scheduled HDFS mover jobs. This will ensure your storage infrastructure remains efficient, responsive, and cost-effective.